Hello everyone, and thank you for watching. Today we're going to talk about the engineering design process and how you can use it to tell your team's story. Before we start, I just want to thank Dr. Carl Crane, who provided permission for me to use and modify some of his slides. All right, to kick things off, I want to introduce myself. My name is Dan Frank, and I am a mentor for both FTC and FRC teams. I'm also the advisor for the Desert Wave RoboSub team. I founded a couple FTC teams here in Arizona, the Geese of Freedom, which is a brand new team this year, as well as the Navajo Code Writers. And I've also mentored FRC back in Florida for about 7 years. My background is in mechanical engineering. And as a graduate student, I also helped the University of Florida win 2 world championships in autonomous boat competitions. There are a lot of ways in which the engineering design process can be defined. For example, the Accreditation Board for Engineering and Technology, ABET, defines it this way. Engineering design is the process of devising a system, component, or process to meet desired needs. It is a decision-making process, often iterative, in which the basic sciences and mathematics and engineering sciences are applied to convert resources optimally to meet a stated objective. Among the fundamental elements of the design process are the establishment of objectives and criteria, synthesis, analysis, construction, testing, and evaluation. All right. It's kind of a mouthful. So let's take a look at a different interpretation of the design process. All right. So that last one was more of a text-based or wordy way of describing the design process. This is a more visual way. And the way to read it is you start off with some kind of vision or problem, you come up with a concept, and then you get into this, kind of really busy or messy process of designing and building, which you're going back and forth, back and forth, back and forth. And at some point, you're going to end up with a product. And we're like, okay. Another interpretation looks more like this. So we have, on the left, more uncertainty. And then as we start to move to the right, we get a greater clarity and focus. All right. So this is where we start off in the design process, and everything is kind of murky. We don't really know what's going on. We do some more research. The problem starts to become a little bit more defined. The uncertainty starts to go down. We make a prototype, and then eventually, towards the end, we have one clear design. So how do you actually learn how to design? Well, so say you're this typical engineering student, and you've got a nice, firm background in science and mathematics. So you've taken physics, you've taken chemistry, you've taken all the mathematics courses, calculus, etc. So you have all these tools that you can use to help you in the design process, all right? So here's the design swamp, all right? And as a student, you're going to go from this solid ground of engineering science, and you're going to make a voyage into the design swamp, and you're going to hope that what you have, the skills that you've learned in those classes, is going to be what you need to actually do well. So typically, the way that design has been taught, unfortunately, is you have some design professor or instructor who takes that student, pushes them off the cliff, and hopes that they do well. Okay, not the best method of doing it. A better way to do it would be to provide them with some design skills, so that way when they do get to that swamp, they're able to navigate it well. That being said, teaching design is a very difficult thing. It's been said that teaching someone how to design is like teaching someone how to paint. We can show you how to set up the easel and how to hold the brush, but it'll take a lot of practice and experience to become a Van Gogh. Okay, so there's a lot of things that we can teach you in order to help with that process, but ultimately you need to actually engage in the design process in order to become proficient with it. All right, so welcome to the world of open-ended problems. Imagine that you're in high school and you're taking physics, and your teacher asks you to do a number of problems from the book for homework. You go ahead and do them. You look up the answers in the back of the book. You see that you got the correct answers, and then you can give yourself a pat on the back knowing that you did a job well done, and you can move on with your life. Those are considered closed-ended problems. There's a question that has one solution. In engineering design, you don't really have the same situation. You have open-ended problems, which means that there are, essentially an infinite number of possible solutions to the same problem. Okay, if you are designing a robot, to accomplish some task, there's a lot of different robots that you could design for that, right? There is no back of the book where you can look up, this is the definitive best design for the robot. And so things start to become a little bit unclear. How do we find what the best answer is? Is there even a best answer? What does best mean? All right. And so for a lot of students who are working on these open-ended problems for the first time, this can be kind of a strange situation where all of a sudden you start to become unsure. Is this really the best design that we could go with? And the answer is you may not know. Even if you build the best robot and it wins the championship and all of that, there's nothing to say that somebody else, could have designed an even better one, right? Just because it's the best right now doesn't mean it's going to be the best forever, and doesn't mean that it's the best that ever could have been. Okay. So this is another interpretation of the design process. This is NASA's best engineering design process. And I like it because it's relatively simple. It uses language that I think is commonly used. It's a little bit less wordy than the ABET definition. And it also has a cool visual to kind of give you an idea of how it all flows together. So there's essentially 7 steps. There's the ask phase, imagine, and then you go in this loop of planning, creating, testing, improving, right? And this can go on indefinitely. And then eventually at the end, you're going to have a final product which you're going to share with the rest of the world. And so the best way for me to actually, describe how this process works is to just give you an example. All right, so let's start with the ask phase. And to do this, I'm going to tell you a story. And this is a true story about a robotics team that I was on that we competed in the Robot X competition. And so part of that competition required us to somehow move, a number of racquetballs from a boat out in the water into a floating target. So you can imagine that there's 4 sides to this target, and each side has a different symbol, and the boat somehow had to figure out which symbol to go to and move the racquetballs either into the big target for less points or the smaller target for more points. So when you're in this stage of identifying the problem, which is the first part of asking, you want to be very vague, okay? You don't want to say things like, we need to make a device that is going to launch the racquetball from the boat to a target. And the reason why you don't want to say, the word launch is because using that word launch, we've already constrained the number of possible solutions that could be out there. Maybe you don't want to launch the ball. Maybe you want, a robot arm to pick up the ball and place it inside, So you want to be as vague as possible so that way you have, the largest number of potential solutions. Eventually you will start to narrow it down, but at least when you're starting, you want to start broad. So we identified the problem as, we needed to move a racquetball from the boat to a target, okay? And again, we wanted to be as general as possible. We didn't want to say things like the racquetball should be flung, for example. All right, once you've identified the problem, then you can start to define it. And here's where you actually want to start being a little bit more specific. You're not necessarily talking about how you're going to accomplish it, but you're talking about how you are going to measure whether or not you've accomplished your goal. So you're asking questions like, what are the objectives and goals? What are the must and must nots, wants, don't wants? What are the constraints, the criteria to evaluate the design? And you're coming up with the specifications. You don't want to use a specification like it shouldn't weigh too much, right? That's a very vague specification that, depending on who you ask, they could give you a different answer, right? So if you finish your design, you say, okay, do you think this weighs too much? And you give it to somebody, they may say yes or no, depending on their own personal preference. Okay, so it has to be something that is easily quantifiable and something that's not up to interpretation. So here's how we define the problem. We came up with a list of specifications. These are all very specific in the sense that they could be measured and that they would be easy for multiple people to agree on. There was no room for ambiguity. So the first one we came up with, it had to be waterproof, IP55 or greater, so that was the way we were going to quantify it. This is going to be on a boat, so obviously it makes sense that it could get wet, and we want to make sure that it would be active and would work, you know, whether it gets splashed on or whether it gets rained on. We wanted it to be able to deliver 4 racquetballs in 30 seconds. You know, notice we didn't say it must deliver 4 racquetballs quickly, because again, quickly is all relative. It had to fit within a certain volume. You know, we only had so much space on this boat, and so we didn't want to devote all of it to the racquetball launcher, so we had to keep it within a relatively small footprint. We also had a weight payload, so a weight constraint where we could only have so much weight on the top of the boat, so it had to weigh less than 20 pounds. We wanted to be able to move one ball at a time, you know, so that way it could shoot a ball, and if it misses, it would have a way to reevaluate and re-aim. It had to be able to be reloaded in 5 minutes or less while the boat was in the water. That was extremely important, especially during testing, where, you know, we don't want to have to spend an hour putting the racquetballs back in the racquetball launcher. We didn't want to use pneumatics, so we said it had to use electric power. It had to be able to, you know, launch the ball from at least 10 feet away. Couldn't cost more than $300, and it had to have a 90% success rate. When you're trying to figure out your specifications, you know, these are some of the areas that you could look into. You know, does it matter how strong it is? Is cost going to be an issue? Typically, cost is always an issue. Do you need to worry about the shape or size of it? You know, how much it weighs, how stiff it is, you know, how much noise it produces. You know, these are just kind of, you don't necessarily have to go through all of them, but these are just kind of ideas to kind of spark, you know, potential constraints that might come to mind. All right, so we were done in the asking phase. Now we're going to start to imagine. So the first part of imagining it is researching ideas. And there's a lot of different ways that you can get, a lot of different sources that you can get information from. So that could be technical reports, you know, internet searches, trade journals, patents, catalogs, handbooks. You know, you can talk to people, okay? You know, when it comes to, you know, FIRST Robotics, you know, you could look up to see what's already been done. You know, you can go to forums like Chief Delphi. You can go to YouTube and look up, you know, videos of what people have done. You know, especially you can look into past games. You know, if you have to pick up a ball, you know, they've picked up a ball in so many games. You know, there's only so many ways to pick up a ball. So look up, you know, other games that had balls and do some research there. There are some problems in gathering information. You know, where can you get it? How to get it? How accurate and credible is that information? Is it still relevant? You know, what decisions result from that information? When do you have enough? These are all different things that you're going to have to kind of grapple with when you're going through the research phase. Especially the one is, how do you know when you have enough? And it's kind of like the same situation as when you're studying for a test is, you know, how do you know when you study for a test enough? Well, sometimes you don't know. And the same is true here. You know, sometimes you're doing research in a topic and you don't know. Maybe if you had done, you know, 1 more hour of research, you would have found something that would have made, you know, a world of difference in your design. And you know, that's kind of unsettling, but that's just the way things are. You know, you do your best and you hope that you cover everything, but you also have to, you know, acknowledge that you may not be able to find everything. All right, so you've done your research. Now it's time to start coming up with solutions. And there's all different ways you can come up with solutions. One is to use adaptation. And adaptation is when you use a solution of a problem in one field and apply it to a similar problem in another field. So for example, one of the things we looked at when we were trying to figure out how to launch a racquetball would be, you know, a pitching machine. You know, what are other devices that launch balls? You know, so like a softball pitching or a baseball pitching machine were, you know, examples of what we might look at. Another approach you can come up with solutions is brainstorming. It's where essentially you gather a group of people, who are familiar with the general nature of the problem, and basically just start throwing out all the ideas you can think of. So you have to have some rules, so no judgments. So you can't, if somebody comes up with some crazy wild idea, you can't tell them, no, it's a dumb idea, you should never talk ever again, right? Because obviously if you do that, right, they're going to clam up and they're not going to say something. And let's say, give you the benefit of the doubt, maybe their idea was kind of crazy, didn't make any sense. However, maybe the next idea they come up with is brilliant, right? But because you basically made them feel bad and they start to shut down, they're gonna doubt themselves and say, well, the last idea they said it wasn't very good, so I don't know about this new one, so I'm just not gonna say anything. So you always wanna make sure people feel comfortable so they can share their ideas. And you want to go with unconventional ideas, right? Because even if that idea specifically is not very helpful, it might inspire somebody else to come up with another idea. And I'll give you an example. When we were first designing, the payload of this boat, so, the boat we were actually given, but everything above we had to design ourselves. And so we had to figure out, what is a way that we can make an enclosure that's waterproof for all the electronics and sensors and all that kind of stuff. And so, some of the stuff we had like these acrylic holes that we put the cameras and stuff in, but those were way too small to put like the computer and, all the other, electronics. So we were like, well, we need something much larger. And so we looked into waterproof boxes, and they were pretty expensive and they weren't exactly aerodynamic. You also keep in mind, this actually not only had to go out in the water, but it also had to be able to go on the highway, because we'd be towing this thing from the lake to the school. And so we're thinking, well, what else is there? And then I kind of made a joke, when I was younger, we used to go on vacations with my family, and there were 6 of us. And so in order to fit all of our luggage, like in one minivan, we had to get one of these, roof carriers and stick it on top of it. And I said, well, what if we just get one of those? Those are already designed to keep the rain out. They're designed to go on the highway. There's plenty of space. They're not super expensive, and I kind of meant it as a joke, and then everyone laughed. And then there was kind of this awkward silence in the room, and everyone's just looking at each other, and they're like, we actually don't have a good reason why that's a bad idea. It sounds silly, but hey, if it works, it works. And so that's what we ended up doing, and it turned out great. So again, don't be afraid to say some wild and crazy things. You never know which idea might be the one that ends up being a winner. And again, the more ideas, the better. So the more options you have available, the odds of having a good one go up even higher. One more way that you can come up with a solution to the problem is through functional synthesis. Essentially, the way this works is you break down what are all the functions of the device that it has to do, and then you look at what are different ways that you can address these different functions. So to give you an example, we knew that we had to be able to move the ball somehow. We had to be able to feed the ball to the mover, and we had to keep track of when the ball has been moved. And so we started, coming up with all these different ideas of just how to move the ball. We can use flywheels, we can use a catapult, we could use a robot arm, air cannon, we could just have a ramp and let the balls roll in, all right? And then we looked at, well, what are all the ways that we can feed the ball to the mover? We can have this kind of carousel mechanism. We can use a linear actuator, it could be gravity fed, conveyor belt, we can use a solenoid. And then finally, how do we keep track of when the ball has been moved? We could either just let it be open loop, we could use IR sensors, have some mechanical indexer, okay? And so the idea is that you have all these different potential solutions to address these different functions, and you can mix and match them, all right? And so maybe you pick number 1 from this and combine it with number 3 for that and do number 2 for that. And the idea is that all these potential combinations now become new design solutions. All right, so we decided that we were going to go with a flywheel method to move the ball. So now that we've done that, we started looking at, what is going to be the best way to move the ball or to feed the ball into the launcher? And so we had three different options. We had the carousel, we had a linear actuator, and we had a conveyor belt. All right, so we're done imagining, and now we're moving on to the plan phase. So now we're in the plan phase. When you're starting to plan, you can start with something as simple as drawing a sketch. For our conveyor belt, we just use this really, simple drawing of, conveyor belt. Here's the racquetballs, here's the flywheel, and they're just going to be, rolling on in there. Okay, it doesn't have to be something super complicated, at least not when you're first starting. Once you had more time and you had a chance to actually develop the idea a little bit more, then you can look at CAD as kind of the next step. So for our carousel design, we actually made this CAD model to kind of show you how everything fits together. So the idea is that this motor would spin, right? And that wheel would roll the balls through the racquetball launcher. We liked it because it had a relatively small footprint, right? You could go up vertically. And so that was one concept that we had. And then we also had one that used a linear actuator. And so there would be a piston that would basically go in and out, which would cause the balls to drop down and be pushed into it one at a time. So now that you've had a couple of different design solutions that you came up with, it's important to figure out how you're going to actually move forward. So which ones are you actually going to choose to actually go into the prototyping phase? A lot of times you have a limited amount of resources, whether it be time or money, so you can't build everything. So how do you prioritize which ones you think are going to be the best ones moving forward? And so one way you can do that is by using a decision matrix. And the way it works is, if you go over here, we've got a number of objectives. These are basically the criteria in which we are going to be evaluating the different designs to figure out which ones do we think are the most promising. So for us, we thought the cost was going to be important, the speed. So by speed, it's how quickly it can launch all 4 balls. The footprint, how much space is it going to take up on the boat, how complex it is, as well as its consistency. So all of these objectives are going to be what we're going to be evaluating the designs on. If we go to the weighting factor, this basically tells us how important each of these factors is when we're evaluating it. So for example, the cost factor is 0.05 and the consistency is 0.3. So what that tells me is that we are basically weighting the consistency 6 times higher than that of the cost. So basically what we want is, we want a device that is going to be extremely consistent, even if it means it not being very cheap. Okay, so we'd rather have an expensive, consistent launcher than a cheap, inconsistent one. The parameter value essentially tells you what the units are of the objective. So when we are measuring the cost, we're going to be measuring in terms of dollars. Speed is in terms of seconds. And again, you'll be thinking, well, seconds is not a measurement of speed. What we mean by speed is how quickly can it launch all 4 balls. The footprint is in inches squared. Complexity is kind of hard to quantify, so it's based on your experience. And then finally, the consistency we are measuring as the delivery percentage. And from there, we have all 3 concepts. We've got the carousel, we've got the linear actuator, and we've got the conveyor belt. Okay, and so each of these has these 3 columns: magnitude, score, and value. And so the way they work is this: magnitude is the actual measured value for that particular objective. So for example, for the cost, we said it costs $25 in order to build that design. The linear actuator was $150, and then the conveyor belt was $500. For speed, we said that we thought we could launch 4 balls, or we thought we could launch all 4 balls within 4 seconds. Okay, the footprint, 105 inches squared. Complexity, we thought it was medium in complexity, and then finally we thought it was about 70% consistent. And sometimes, these numbers, you don't actually have the device built, so it's hard to say, well, how consistent is it actually going to be? And so sometimes you just have to put your best guess in order to fill in this table. From there, you're going to assign them a score. So for example, the carousel was the cheapest one out of $25. So we gave it a score of 9, and so this is at base out of 10. Okay. The linear actuator was the second cheapest, so we gave it a score of 6, and then The conveyor belt was the most expensive at $500, so it got a score of 3. The value is basically when you take that score and you multiply it by the weighting factor. So 0.05 times 9 gets you 0.45. You do that for each of the objectives, and then you add them all up, and then you get your overall value. So in this case, the carousel got a score of 7.5, the linear actuator got a score of 8.2, and the conveyor belt got a score of 3.55. Now, you may be looking at this and say, wow, this is great. You know, it's very objective. It's very clear on which design is going to be the best one. But you have to be careful because it can be a bit misleading. For example, the linear actuator had a magnitude of $150, whereas the carousel is only 25. So the linear actuator was basically 6 times more expensive, but it got a score of 6, whereas this one got a score of 9. Right? So the score is not 6 times lower, right? And the same thing with this one. This one's, you know, $500 compared to 25, and it's got a score of 3. The score is only a third of what this one got, whereas it probably should be a lot lower, okay? And so the reality is you can kind of fudge these numbers any way you want to make any one of these the winner. So you got to be careful. However, where it is very valuable is that it shows where your priorities lied when you are assigning the objectives. So again, basically, these weighting factors say a lot about how we are designing this device. You know, we're basically saying that consistency is going to be, you know, one of the most important factors, whereas cost, we're not so much concerned about it. Speed was important. The footprint, you know, was not as important. And then we also didn't want it to be super complex because complexity is also tied into reliability in many cases. So, looking at this, 7.5, 8.2, it's really hard to pick a clear winner here. It's pretty much too close to call. So we decided that we were actually going to end up building both of these. Now, over here, where it is also important to, or also useful, is that this guy wasn't even close. The conveyor belt score of 3.55. You know, looking at these numbers, these are too close to call, but you know, if you had to cut corners and didn't have, you know, all the resources to build all 3, it's pretty clear that this is probably the one that you should avoid. All right, we're done with the planning phase. Now it's actually time to create something. So we built a very crude prototype, just with stuff that we had lying around. We had some trolling motors that were sitting on a shelf that we were able to turn into flywheel motors for our racquetball launcher. We mounted to a wooden board, and that was our first prototype. All right, now to test it. So here is the first test of the prototype. So it's doing pretty well. It's not as consistent as we would like, but you know, part of that is we're not able to consistently put the ball into the launcher, right? Depending on, you know, what angle they're pushing through or how much force they're pushing behind it, it's going to cause the ball to move in a slightly different trajectory. All right, so we did some tests. It was looking good. Now it's time to improve it. Right, so we needed some way to automate the feeding of the balls into the launcher. So we went ahead with the linear actuator prototype. So once we've improved it, now we got to go back and test it. So here's a test of the racquetball launcher now with a feeding mechanism.
Go ahead and drop it. Go for it.
Told you it was the lip.
Yeah, it's the lip. Go ahead.
Well, so far we're testing both, but this is current.
So it's definitely an
This
improvement,
system we think will be easier to
but
when it's
we were having some issues with it getting jammed. And as you can see, like one of the students, they had to like help it out every time it pulled back because it was doing weird things. So we need to come up with another idea. So we went back to the create phase and we decided to build the carousel. All right, so that's what that one looks like. And we actually designed this plate right here to be able to integrate both with the carousel design as well as the linear actuators. So if you look at it, this plate is identical for both of them. And we did that on purpose because we knew that we didn't know exactly how we were going to get the balls into the racquetball launcher. So rather than having to design two totally different, mounts for the motors, we decided, well, let's just make one plate that you can attach either design to. Okay. So we created a new prototype. Now it's time to test it. So here is the carousel in action.
It's gonna be rapid fire, Lucas. You ready?
I'm not even gonna try and test.
3 balls.
Yeah, there's a gap.
So as you can see, it did pretty well. All right. So we took that, we improved upon it. And so that was our final design that we stuck on the boat. Okay. And we went ahead and we tested it once more. So this is the carousel launcher on the boat.
Yep.
And then we've got a student in the background with a garbage can trying to catch them to see how accurate it is. And it's doing pretty well. All right, so we've gone through this process a few times, okay? And it's important to note that you could always go back to these other steps too. Sometimes you may decide, hey, we didn't define the specification the way we needed to, or sometimes you get to a point where it's like, man, we just need to go back to the drawing board and start fresh. And so you may go all the way back here. That's okay. Engineering design is a messy process. But once you have done enough testing or you run out of time and you need to show your final product, you can share it. You want to communicate the results. And again, you don't have to wait to the very end to communicate results. Sometimes you want to give like a report, in the progress, to show the progress of what you've done so far. Okay, and for us, it was important to do that earlier on, with our CAD model, so that way we could get funding to actually buy the parts that we need to make the prototypes. So CAD is an extremely useful tool because it allows people to see what you're working on before you actually have it built, and it can get them excited about your design and want to potentially help you fund it. All right. So design is a messy, iterative process. Before I said that was the final design of When the Boat, it's actually not quite true. We actually decided not to go with the carousel, and the reason why is because it was too difficult to reload the balls on the water. And so we ended up going with an improved linear actuator design. So here's the racquetball launcher actually out on the water. You can see the target. The cameras are identifying which target to aim in. And you can see the racquetball launcher right here, shooting the balls in. And so it was a pretty exciting project to work on. It was a lot of fun. And we actually went on to go to Hawaii, which is where the competition was, and we won that competition. So engineering design is just like telling a story. You may have heard of the monomyth or the hero's journey. It's essentially a formula that has been used for years and years to tell variations of the same story. Everything from Harry Potter to Star Wars to Hunger Games, Lord of the Rings, they all kind of follow the same formula and the story, and it's just a matter that the details are different. So for your team and your season and the design of your robot, you are also going to tell a story. And the formula that you are going to use is the engineering design process. Okay. Now, you want to tell a convincing story to the judges during your season. All right. Imagine that you had never seen the Harry Potter movies or read the Harry Potter books, and you ask your friend, you say, hey, what is this Harry Potter story all about? Can you kind of give me a summary of what happens? And the only thing that they told you was the epilogue, or like the final few pages of the series. all right, that would not be a particularly satisfying answer to you, right? That would be, you wouldn't understand why everyone loves Harry Potter so much, right? Just by that one explanation. And the reason why is because you've left out all of the struggles that the characters go through, all of the high points, all of the low points, right? Everything that makes the story interesting, you've kind of just gotten rid of and went right to the ending, right? And it's true for the engineering design process too. When you are telling your story, either to the judges or to, you know, the public or anyone that's interested in hearing about it, you don't want to just say, here's our robot, the end. Okay, that's not a very interesting story, right? They can see your robot. But what they don't know is, why did you make the choices that you did? What challenges did you overcome while you were designing your robot? What did you learn in that process, right? That's the really interesting part of the story. And that's the part of the story that you want to make sure you document in your design notebook. So when I was the coach of a brand new Navajo co-writers team, we made a choice to integrate the engineering design process explicitly into the engineering notebook. And so essentially every time we put a post in the engineering notebook, the students would document, you know, what step or steps they thought in the engineering design process that they thought that post represented. So to give you an example, when the game first came out, you know, we looked into what are all the different ways that you can score points in this particular competition, right? So they had to go into watch the video, they had to look in the manual, and we compiled that, and we consider this part of the asking phase, okay? Later on, they built a prototype robot that had this claw, and the idea was that this claw was to pick up the wiffle balls, right? So this would be the create phase, and didn't go so well. They did some testing. They were having a hard time getting a good grip on the balls. So then they went back to the planning phase. Well, actually, before that, they went into the imagine phase, where you can see right here, they actually did some research on what are some different ways that things can be picked up that they saw in nature. And so they looked at, you know, the mandibles on ants, and they're like, hey, can we do something like that? Maybe we can pick up the balls with something like that. And so they went into the planning phase where they actually designed, you know, something similar in CAD. And then from there, they went into the create phase again, and they actually, you know, 3D printed, you know, one of these claws, okay? And then, you know, one of the students recognized that we didn't have a lot of money because we're a brand new team, and so it might be difficult for us to buy some of the parts we needed. So then they looked into building their own foundry, so that way we could take, you know, soda cans that we found on campus of the school, and then melt them down, and then eventually we could turn, you know, those metal ingots and cast them into parts for the robot. And then we had another student, and they were looking into taking old electronics and devices. So, you know, I think they had a fax machine and a vacuum cleaner that had been donated, and they went ahead and they took it apart, and they went to see if there was any parts that they could take from that machine and then turn it into parts that they could use for the robot. And I want you to keep an eye, or to remember what this wheel looks like, right? And so eventually they came up with this robot, all right? But again, all of this is what the judges wanted to hear about, right? Because it shows all the hard work and all the obstacles they overcame and all the creative thinking that they were able to come up with in order to get to this potential solution, okay? So now the judges have a better appreciation as, why are these claw things on here, you know? And it turns out when they actually tried to pick up the balls using these claws, but it wasn't working so well. So they said, well, you know, now that we have them, is there anything else that we can use them for? And so they try to find, you know, other creative ways to use the parts that they had if they weren't working the way that they were intended, okay? So that's how they told their story. Every good book deserves a sequel. So I just wanted to show you, you know, what they've been able to do within the last couple of years As you can see, you know, the complexity of the robot has certainly grown, as well as the sophistication. You know, now they have their own custom, you know, 3D printed tank treads, but still true to form. You know, they're still using parts of that vacuum cleaner. This wheel right here is actually the same wheel that was on the vacuum cleaner. So they've come, you know, they've come a long way in just a very short time. So I wanted to thank you all for watching. I'm hoping that this gave you all some ideas of how you can take the engineering design process and not only help you throughout the season with designing your robot, but also with sharing your story with the community. So feel free to leave comments. Good luck to you all this season, and I can't wait to hear all of your stories.